In this video, we are going to discuss solve problem 5.4, riding a bicycle. The problem says a bicyclist goes down a 4.2 degree slope at a steady speed of 5.1 meter per second. Assuming a total mass of 82.2 kilogram, bicycle plus rider, what power output must the cyclist expend to pedal up the same slope at the same speed? Let us first write down what the question has given us. They have given you the angle theta of the slope, which is 4.2 degree, the steady speed at which he goes down the slope, which is 5.1 meter per second, the mass of the bicyclist plus the cycle, which is 82.2 kilogram, and we need to find what power must the cyclist expend to move up the same slope with the same speed. Power output can be calculated by taking a product of force and velocity. Question has given me the speed v, but what force must the cyclist apply to move up the slope with the same speed? To solve this question, we need to do the analysis of force acting on the bicyclist when he is coasting down as well as when he is going up. Then we can use that analysis to find what is my force F. So let's start with the first case that the question has described when he was coasting down. Coasting means to move without applying any force. So coasting down means the cyclist was coming down without pedaling, without he applying any external force on the bicycle. So let's look at the forces acting on the bicyclist in this situation. If he's moving down with speed v, the force acting on the bicyclist will be first the force due to gravity mg acting vertically down. Then you have the normal force perpendicular to the surface, and you will have the force of friction plus all the resistant forces like the air drag, air resistance, whichever force is opposing this motion. Then we split the force due to gravity into its component. First component along the y-axis, mg cosine theta, then one along the x-axis, which is mg sine theta. Since coasting down means without applying the external force, mg sine theta and the force of friction are the only two forces acting along the x-axis, which is causing the bicycle to move with a steady speed. If the speed is constant, or steady, that means my acceleration will be zero. And if your acceleration is zero, that means the net force acting along x-axis will also be zero. I'm going to use this equation of net force to find a relationship between force of friction and mg sine theta. So let's calculate the net force along the x-axis. Net force along the x-axis is nothing but sum of the forces along the x-axis. With the ones going to the right, I take as positive, and the one going to the left, we take as negative. So this I will write as force of friction minus mg sine theta. Net force is 0, so force of friction minus mg sine theta is equal to 0 here. And when you rearrange the term, you can write the force of friction to be equal to mg sine theta. So from the first part of the question where the bicyclist was coasting down, I determined what is my force of friction. And this expression for the force of friction I can use in the second part when I'm analyzing the forces acting on the cyclist when he is going up. So let's start discussing the second part. In the second part, the cyclist must pedal up, and he must pedal up with the same steady speed. And we are going to analyze the forces acting on the cyclist when he is going up. So let the cyclist go up this time with the same speed v. We will draw the forces again here. Gravity acting vertically down, the normal force, then the force of friction. Since the cyclist is moving up, force of friction will be acting down. Then we split gravity into its component, mg cosine theta along y-axis and mg sine theta along x-axis. Now you must notice, in order to go up at a constant speed, the cyclist has to overcome two forces here. One, the force of friction, and the force mg sine theta, the x component of force due to gravity. The force applied by the cyclist must be equal to the sum of these two forces. Only then can he move with a constant speed. So my F applied must be equal to the force of friction plus mg sine theta. In the first part, when we discussed coasting down, we found the force of friction to be equal to mg sine theta. So I will write that for force of F friction mg sine theta plus mg sine theta. So that gives me force applied to be 2 times mg sine theta. And once I get my value of force, I can calculate the power. Power P is F times V. So 2 times mg sine theta into V. Then we substitute 2 times 82.2. G is 9.81. Sine 4.2 into V, which is 5.1. And when you solve this, you get the value of your power as 602.39. You can also write this power in kilowatt by dividing this number with 1000, and then you get the power as 0.6 kilowatt. Sometimes they ask you to convert the expression for power from watt to horsepower. And we can do this by using the relationship between watt and horsepower. We know that 1 horsepower is equal to 746 watt. So if I want to convert my power from watt to horsepower, I will just divide this number with 746, which you can do as 602.39 divided by 746, and that will give me my power as 0.81 horsepower. So to summarize this problem, what we essentially did was found the force of friction by taking the first case when the bicyclist was coasting down with a constant speed. Coasting down again means to move without applying any force, to let the forces on the slope do the work on you. And when we found the force of friction, we substituted the value of this force of friction when we considered the forces when the bicyclist was moving up with the same speed. When you do the force analysis on the bicyclist, you see that for the cyclist to move up with a constant speed, he must overcome two forces, force of friction and mg sine theta. So the net force the bicyclist must apply is a sum of force of friction plus mg sine theta. That gives me 2 times mg sine theta. Use this force in the expression for power, and you can calculate the power shown here. Once you get the power, if they ask you to convert this from watt to horsepower, use the relationship between them. 1 horsepower equals 746 watt. So divide the number in watt with 746 and you will get your power in horsepower.